Welcome to Design Campus Layer 2 Infrastructures. If we look at the ENSLD blueprint, then we do see that Cisco specifically calls out these campus infrastructures as being Layer 2. And as such, in this video series, we're going to explore all of the different elements of a Layer 2 deployment out to the edge, including spanning tree configuration, as well as edge services like Power over Ethernet and different types of media. However, we in the real world know that in a lot of cases, we'll deploy Layer 3 out to the edge. Now, it's not a super common deployment, but at the same time, it is absolutely a valid configuration that we want to explore. So also, as part of this skill, we're going to take a look at why we'd want to deploy Layer 3 to the edge, and what are the benefits to it, because there are a lot of benefits to deploying Layer 3, but also, what are the reasons why we might not want to deploy Layer 3? Why would we go with Layer 2 instead? And again, in the real world, we know that most networks are deployed with Layer 2 out to the edge, so there must be some good reasons, and we'll take a look at that. So come along, we'll have a lot of fun exploring how we design campus networks. And with that, I will see you in the next video. Before we can even talk about Layer 2 or Layer 3, we need to start at Layer 1. We need to be aware of all the different media types that are available to us for building our campus infrastructures. And if you're maybe thinking about, well, Jeff, what is there to know, right? I mean, we got copper, we got fiber. Hang on and watch this video all the way through, because there have been some advancements in the transceiver world these days that you might not be aware of. Let's take a look. Let's start with the world of copper. In a lot of our experiences, we understand that copper Ethernet is supposed to go up to 100 meters. But this is going to depend on the cable type as well as the speed that we're trying to communicate at. For example, if we want to go 100 meters on 100 meg Ethernet, then we only need a Cat5 cable in order to make that happen. But if we want to do that on a gig, then we need to make sure that our connections are at Cat5e. This is why over a decade ago we were ripping out all of our Cat5 cables in the walls and putting Cat5e in. It was to support 1 gig out to the clients. Well, now 1 gig is yesterday's news, and so we want to go 10 gig out to our clients. But if we want to go 10 gig, we're not going to be able to do that on Cat5e, at least for 100 meter runs. Instead, we're going to need Cat6a cabling. Now we can go 100 meters on 10 gig once again. All of these cable types are going to use the standard RJ45 connection type, which is how we're going to connect to most of our end devices off of the access layer. But this, by and large, is not how we connect to other switches. And for that, we are going to turn to fiber connections. Now, we have two different types of fiber. We have single mode fiber. This would be for longer range connections. In other words, between buildings is usually what this looks like. And then we also have multi-mode fiber. This would be for shorter range connections, so think about switches within a building. And on Cisco switches, anytime we're talking about a fiber connection, we're going to be talking about using a small form pluggable connection type. This is a modular slot that's going to allow us to plug in whatever type of optic or transceiver that we want. This gives us modular capabilities so that, for example, if Cisco were just to give us a single mode fiber connection type on a switch, but what we need is multi-mode fiber, well, that's going to cause us a lot of problems. Instead, Cisco gives us an SFP slot so that we can plug in whatever transceiver type we need, whether it's single mode fiber, multi-mode fiber, and Cisco even gives us the ability to connect in an RJ45 transceiver. But here's a key point. Whenever we're talking about SFP slots, this is only for 1 gig connections. So if we're going to be looking at 1 gig optics, then we need to go out to Cisco's website and find out what transceiver types they make for 1 gig applications. Now you might be thinking, okay, well wait a second, Jeff, I know that we do 10 gig on SFP slots. What's up with you saying it's only for 1 gig? When we talk about doing 10 gig on SFP, that's a little bit of a misnomer, because really what we're doing is we're leveraging SFP plus slots. The SFP plus slot is the exact same form factor as an SFP, except now it can support 10 gig. And therefore, we kind of get mixed up sometimes in our vernacular in saying that it's an SFP 10 gig connection. Really, it's an SFP plus 10 gig connection. Just as with our 1 gig SFP slots, we're going to have to decide between multi-mode fiber and single mode fiber. And very importantly, if we're looking at multi-mode fiber, we're going to care about the quality of that multi-mode fiber. And the reason we care about that quality is for the same reason we care over here with copper about what type of cabling we have in the walls. Because in the world of multi-mode fiber, we might have OM3 in our walls, and on OM3 we can go 300 meters on 10 gig. But hey, if 300 meters isn't enough, we can improve the quality of our fiber, maybe deploy OM4. And OM4 is going to give us 400 meters on that 10 gig connection. Now there's only one spec of single mode fiber, so we don't need to worry about this concept in the long range world, but as far as short range is concerned, when we're connecting to other closets within our building, then this quality conversation is absolutely something we must keep in mind. Now this SFP Plus world actually gives us 2 other ways that we can connect using these module types. The first of which is going to be a Twin-X cable. The Twin-X cable is a pre-terminated cable. It's actually got the SFP Plus connectors built onto a copper connection. Now on most Cisco switches we can support Twin-X connections of up to 10 meters, but on some we can only support connections of up to 5 meters. And we have to be careful when we order our Twin-X because there's nothing we can do to increase the length of these cables after we've ordered them. Because again, the ends are pre-terminated. So we take this cable, we just plug them into the SFP slots on one switch, run it over to the other switch, which again, within 5 meters or 10 meters is going to be in the same closet, and we're going to connect the other end into the other switch. Now there is one other type of cable that's very similar in nature, and that would be an active optical cable, or AOC. The AOC is going to look exactly like the Twin-X, other than instead of using copper, we use fiber. The primary reason we'd want to use an AOC over a Twin-X is if there's a lot of electromagnetic interference inside the closet. Because electromagnetic interference will affect copper, in other words Twin-X, but it will not affect optical connections. So you'd say, well, why wouldn't we always go with AOC? Well, AOC is going to be more expensive than Twin-X. Twin-X is actually a very inexpensive way of connecting our switches at 10 gig. And that will be our primary motivator for deploying Twin-X. And I can tell you in the real world, I've deployed a whole lot of Twin-X, and I haven't deployed a whole lot of AOC. You really have to have a strong reason for going to that to justify the cost difference. Now, similar to SFP+, we have this concept called QSFP+. This Q stands for quad, which means 4. And so what a QSFP+ is, it's a transceiver that supports 4 different SFP+ streams all at once. Now, if we do the math, 4 10 gig connections, well, this is going to be a 40 gig stream. Now, pretty much everything we said about SFP+ is going to apply to QSFP+, but here are a few things we need to keep in mind. First of all, regarding the fiber type, we do still have single mode and multi-mode options, but if we're going to run multi-mode on OM3, for example, we're only going to go 100 meters on a QSFP+ interface. OM4 will get us a little bit more, we can go 150 meters. We can see we lose a lot of distance by using QSFP+ connections. Additionally, QSFP+ is going to be a slightly larger form factor than an SFP+ connection. So importantly, we cannot mix and match SFP+s and QSFP+s. They're not backwards compatible with one another. Now, we're still deploying a lot of 10 gig and 40 gig out there, but something happened in the industry a few years ago that went unnoticed by many network engineers. And that is that the industry evolved to new form factors, SFP28 and QSFP28. The SFP28 interface is designed to replace the SFP+ while supporting 10 gig and even 25 gig. The SFP28 is capable of supporting 28 gig of throughput, but once you take the encoding into account, really what we're getting is closer to 25 gig of throughput. This has the SFP+ form factor, and that's important because that means that we can slide SFP+s into SFP28 interfaces. So we have backwards compatibility on that front. Similarly, QSFP28 has the same capabilities in that it can run 10 or 25 gig, but now it can run 4 of those streams at once. So if we enable those at 10 gig, well, 10 gig times 4, that gives us 40 gig. So QSFP28 is the new 40 gig interface, and it has the same form factor as the QSFP+s, which means we're backwards compatible. We can plug QSFP+ optics into a QSFP28 interface. But wait, there's more, because we can enable these QSFP28 flows to be 25 gig each. And at 4 of them, that gives us 100 gig. This is the new 100 gig interface type as well. But wait, there's still more, because if we take those 25 gig flows and only activate 2 of them, well, that gives us the ability to enable 50 gig communications. So you may have seen some switches out there that support 50 gig, and this is the reason why. Because it's pretty seamless for us to enable 2 of these flows at 25 gig apiece. And even though it might not seem much more than 40 gig, well, hey, that's still a 25% increase. And it might make more sense from a cost perspective to deploy 50 gig instead of 100 gig. Now, just like the traditional 10 and 40 gig world, we need to pay attention to single mode fiber and multi-mode fiber connections. And yes, with multi-mode, we have to worry about the quality still of the different types of fibers that we're deploying. And on top of that, we have Twin-X and AOC options available to us. Now, one warning here is if we're going to deploy 100 gig via multi-mode fiber, we need to pay special attention to the type of fiber connection that's going to take. Most all of these connections are going to be an LC fiber type, but certain 100 gig optics are going to use what we call an MPO-12 connector type, which is completely different, and that's going to require us to use more than 2 strands of fiber in order to connect us at 100 gig. The more modern transceiver types are going to use LCs, so in most cases we'll be fine. But again, from a design perspective, something that can absolutely fall through the cracks would be the type of fiber that we need in order to connect these transceivers. In the English-speaking world, we call this dotting our I's and crossing our T's because there are some details that can just fall through the cracks in our designs. So let's make sure we do our due diligence when it comes to that. Now, as design engineers, we should always do our due diligence by making sure that we're deploying the right transceivers and such by going to Cisco's website, check out their data sheets, and check out their transceiver compatibility matrix to make sure that as we're deploying different types of transceivers, that they can actually plug in to the switches that we want to plug them into. And as far as this conversation is concerned, let's first of all keep in mind that we have the traditional RJ45 copper connections. If we want to deploy that at 10 gig at 100 meters, then we need the Cat6A cable types in there. Otherwise, we can rely on Cat 5e for gig and lower. Second of all, our SFP slot options. We have single mode fiber, we have multi-mode fiber, and we need to keep in mind the different quality types of multi-mode fiber that exist. We also have twin-ax and AOCs, and then at 1 gig we have RJ45 as an option as well. Now third, we have the, call it legacy now, SFP Plus and QSFP Plus form factors. That gives us 10 gig and 40 gig on more legacy platforms. And modern day now, as far as Cisco's newest switches are concerned, we're going to see SFP28 and QSFP28. And SFP28, QSFP28, they give us not only 10 gig, but also 40, 50, and 100 gig on the QSFP28 form factor type. I hope this has been informative for you. I'd like to thank you for viewing. There are many debates in the networking world, but probably none more prolific than this idea of whether we should extend layer 2 or layer 3 to the access layer. In this video, we're going to take a look at both options. When it makes sense to deploy layer 2, what are the benefits of deploying layer 2? But then what are the drawbacks? Same thing with layer 3, because the reality is that there's no perfect solution. If there was, then we'd all go with it. Instead, what we are left with is knowing the pros and cons to both options, and then looking at our scenario, our real life scenario, the design that we're creating, and making a decision based on the pros and cons. Let's dive in. In most campus architectures, we're going to have a pair of distribution switches, and those are going to be connecting down to the access layer. And so we're going to have a set of access layer switches that have to connect back, and we have to make this decision about whether this access layer is going to connect back at layer 2 or layer 3. So as we draw this out, what do we need to consider when making this decision? Well, let's think about some of the properties of a layer 2 network. We know that a layer 2 network essentially equates to a broadcast domain. And we know that we can share VLANs among all of the switches in a layer 2 domain. On top of that, we're going to need to rely on spanning tree protocol in order to block loops from forming because, again, in a broadcast domain, we're going to have a lot of broadcast. And we don't want those to be propagated infinitely because that's going to cause major performance issues. I mean, it'll just shut down our network outright if we accidentally loop our traffic. Meanwhile, from a layer 3 perspective, we know that we're going to have to run a routing protocol in order to support layer 3. Incidentally, we're still going to have to configure VLANs, but those VLANs will now be isolated to the switches in the access layer instead of the distribution layer. And this, by the way, includes switch virtual interfaces because we still need default gateways and we're still going to need those VLAN interfaces, but the VLAN interfaces will again live here at the edge. So what are the benefits to deploying layer 2? Well, the key benefit is going to have to do with this, the fact that we have our VLANs spread throughout the domain. We are going to be able to share subnets among our different users at different locations. So regardless of whether a client hangs off of this access layer switch or this access layer switch, maybe on different floors inside the same building, we can have them be on the same subnet, let's say subnet A. But we can already see the big disadvantage to managing a layer 2 network, and that would be this right here, spanning tree protocol. Keeping spanning tree protocol tuned is going to take an ongoing effort. And there's a lot of risk involved in running spanning tree, not because of spanning tree itself. Spanning tree is supposed to reduce our risk, but the risk is tied to this up here, a single broadcast domain. Because we need loops in our environment for redundancy, we have no choice to rely on spanning tree to block those broadcasts from looping around. But I can tell you right now that spanning tree can fall on its face. And if a broadcast loop forms during the day, well, that's going to take our network hard down. So the first and best benefit of layer 3 is the lack of spanning tree. We don't need to rely on spanning tree because there are no layer 2 loops in a layer 3 access layer design. We also get very fast routing convergence times out of these routing protocols. So if, for example, our link goes down here on the left, we can immediately switch over and start forwarding traffic from a layer 3 perspective to the other distribution switch. So great, no spanning tree, no broadcast loops. We don't have to worry about that at all. That is a huge relief in the layer 3 design. But unfortunately, as you can imagine, there are some downsides to this. And there are two primary downsides I want to talk about, and both of them have to do with this concept of VLAN isolation. The first of which is that we can no longer share subnets, like we talked about with layer 2. If we have two clients hanging off of two different access layer switches, then we can put one on subnet A, but the other client can't share that subnet, so it's going to have to be on subnet B. This isn't a huge problem these days because most of our devices at the access layer are designed to be on separate subnets, but this still can come back to bite us. And the question is, even if on day one we do not need to have subnets shared among our different access layer switches and we deploy an entire layer 3 domain, what happens if then all of a sudden we do deploy devices throughout the network that have to be on the same subnet? So there's a lot of risk in migrating to layer 3, not because of what we might find on day 1, but what we might find on day 100. What if something shows up that we weren't expecting? We'd have to convert all of these links back to layer 2 in that case. And yes, this does happen in the real world. I worked with an organization who had to migrate from layer 3 to layer 2 because of this situation, where on day 1 they didn't need layer 2, and so layer 3 was deployed, but after the fact we had need for layer 2. And so we had to go back and convert layer 3 to layer 2. Now the second issue with this that I want to talk about has to do with policy sprawl. And this is an interesting one. Okay, Jeff, what are we talking about with policy sprawl here? Well, if you're working your way through the ENSLD course, then you just got through with the skill called Explain the Hierarchical Network Model. And as part of that, we talked about how policy is attached, in most cases, to those SVIs, those switch virtual interfaces. And the question is, where do those VLAN interfaces live? In a layer 2 design, the VLAN interfaces live here at the distribution layer. And so our policy is defined here on these two switches. But as we discussed in a layer 3 network, the SVIs are going to be attached to the access layer. And so all of a sudden, our policy has to be managed at every single one of these access layer switches. And in this drawing, this isn't a big deal, right? We have 4 access layer switches compared to 2 distribution layer switches. That's fine. We don't need to worry too much about policy sprawl in that situation. But what happens if we have 100 access layer switches? What do we have to manage our policy across all of them? We have to manage the SVIs. In some cases, we might have multiple access layer switches. We may even need to run an FHRP inside of an access closet. So between the possibility of deploying first hop redundancy protocols as well as access control lists to our SVIs, well, all of a sudden we have to manage this across a whole lot more switches in a layer 3 design. So if layer 3 had no downsides, then we'd all migrate to layer 3. But we know that most networks out in the real world are layer 2 to the edge. And we see the reason why. First of all, layer 2 gives us the ability to share subnets across locations, and it also results in that centralized policy model. Keep in mind that we do have to deal with the risk of loops and broadcast storms, and that's never a good thing. But if we consider running to layer 3 for that loop-free design, that's a huge win in the layer 3 column. We don't have to worry about spanning tree, we don't have to worry about loops. Well, we can't share subnets among our access layer locations. And even though we might get away with that on day 1, we have to think about the future. What if something shows up and we have to convert this all back to layer 2? That would be a nightmare. And lastly, the other thing we think about with layer 3 is that concept of policy sprawl. Now our SVIs are out at the edge, and that's where we're going to deploy access control lists. And we might even have to run FHRPs inside of each access layer closet, depending on how many switches are inside that closet. And so it's just things that we have to think about when it comes to deciding between layer 2 and layer 3. There is no wrong solution. Going to layer 3 is fine. A lot of organizations do it. But understand it's not all benefits. We have to think about the downsides of either solution, layer 2 or layer 3. I hope this has been informative for you. I'd like to thank you for viewing. Anytime we're studying for a Cisco exam, it seems like we have to go through the history lesson of where spanning tree came from and all the different versions that we've had of spanning tree. Why can't we just learn what we do today? Why do we have to go back in time? And the reality is that there are a lot of networks out there still running traditional spanning tree. And we might have to upgrade those networks to run Rapid or MST. And so in this video, it's like with a lot of videos associated with Encore and CCNA, we're going to walk through the different types of spanning tree protocol that have existed over time. We need to understand where spanning tree protocol came from as much as anything so we can know the value of deploying the modern protocols. Let's dive in. If you're going for the ENSLD, then you already know the purpose of spanning tree. It's to prevent broadcast packets from looping endlessly within our network. We need loops for redundancy, but broadcast packets don't like to play by those rules. As such, we deploy spanning tree protocol and we block one of these links, place it into a block state, and that prevents the broadcast packets from looping. But how fast does it take for us to converge? For example, with the switch at the bottom, if we lose this link here, how quickly can the switch decide to move over to its backup link? And furthermore, what happens when a link upstream goes down? What if this link up here goes down and now all of a sudden we need to transition the blocking state to a forwarding state in order to allow traffic to flow all the way back around to the root? It's one thing when the failure is directly attached, it's another thing entirely when the failure is an indirect failure. This is what we mean when we talk about spanning tree convergence time. We want the network to converge as quickly as possible. And in traditional spanning tree, this process can take up to 50 seconds. And that's because 802.1d, the original spanning tree protocol specification, it relies entirely on timers in order to figure out what's going on in the network. In other words, by default, I'm going to wait 20 seconds here to realize that those BPDUs are not coming anymore and I've lost my connection to the root. But this is going to take another 30 seconds for me to transition the blocking state back to a forwarding state, hence 50 seconds. And this is where I get my calculation of saying they can take up to 50 seconds to converge the network in the event of a failure. Now, Cisco threw some enhancements at traditional spanning trees, such as backbone fast and uplink fast and port fast as well. And that would certainly help in these situations that we described. Furthermore, Cisco enhanced the original spanning tree in a way that they call per VLAN spanning tree plus. The value of PVST plus is to give me one topology per VLAN. Because in traditional spanning tree, if I'm blocking this link, well, that's an expensive link I might have paid. That could be a fiber optic link, and I get no bandwidth out of it in traditional spanning tree. But with PVST plus, I can block this link in, let's say, VLAN 10, but block this link over here in VLAN 20. That way VLAN 10 can take advantage of the bandwidth on this link, and VLAN 20 can take advantage of the bandwidth on this link. Now eventually the industry got around to coming out with 802.1w, which is what we call rapid spanning tree. The reason rapid spanning tree is rapid is not because of timers. Instead, we move towards a negotiation model. We're exchanging BPDUs differently in rapid spanning tree. They also implemented Cisco's backbone fast, uplink fast, and port fast functionality, so now we can take advantage of some of those features that were exclusive to Cisco. Now we do still have timers in the rapid world, but what surprises a lot of junior network engineers is that the timers are the exact same as they are by default in traditional spanning tree. The reason we have those timers is to fall back just in case we need them, which can be beneficial in a lot of cases, but it also allows for backwards compatibility with traditional spanning tree. Now Cisco has an implementation of this that they call rapid PVST. And the reason Cisco created their own rapid version of spanning tree is because, again, the industry did nothing to address this concept down here of having one topology per VLAN. It would take another industry release of spanning tree in order to fix this, and that would be 802.1s multi-instance spanning tree, or MST. Now, even though the industry likes to copy Cisco's ideas, they don't like to take them directly. And so one of the biggest differences between MST and rapid per VLAN spanning tree is the idea that it's now one topology, not per VLAN, but per instance. An instance is simply a collection of VLANs. So I could assign, for example, VLANs 1 through 10 into one instance and VLANs 11 through 20 to a second instance. What's interesting about this is that if I have 100 VLANs running in a rapid PVST environment, then I'm going to have 100 different STP topologies running Cisco's rapid PVST. In most cases, I only need 2 different topologies. It's very rare I need anything more than that. What I described earlier about saying, down here we'd block VLANs 20 and 10 on different links, that's usually what we end up doing. And so in an MST environment that's tuned, we might find that we only have 2 STP topologies that we need to worry about. This can make a big difference from a resourcing perspective, because the CPU on these devices no longer needs to process BPDUs for every single VLAN. Instead, it only needs to process BPDUs sent on those 2 different instances. So MST improves on the performance of rapid PVST while still running rapid spanning tree under the hood. In other words, has access to all of these enhancements over traditional spanning tree. So here's the question. Why would we deploy rapid PVST versus multi-instance spanning tree? Multi-instance spanning tree seems to have all of the features of rapid PVST, but there is one concern with MST, and that can be that it is complex to manage. It's more complex to set up, it's more complex to troubleshoot, and this issue alone prevents a lot of organizations from migrating to multi-instance spanning tree. However, there is one very important reason why we might want to go to MST, and that would be when we purchase a new switch from Cisco. We've got it out of the box, it's shiny, I love new switches, but then we check the datasheet, we might find that the datasheet tells us that that new switch can only run so many instances of spanning tree topologies. In other words, even though the VLAN support is often all 4096 VLANs that we can run on that switch, spanning tree protocol might only be able to handle, let's say, 256 on a low-end switch. And even some middle grade switches might only support 1024 or 2048. Now in most cases, this doesn't even come up as an issue. However, I can tell you right now, if we were to spin up a 257th VLAN on this switch here that can only support 256 different spanning tree topologies, then we will have a VLAN running without spanning tree. And that is just as bad as it sounds, because we are now going to be managing a looped network topology without spanning tree to block any of those links on that VLAN. So in this situation especially, we would absolutely have to migrate to multi-instance spanning tree. Although hitting this limitation in the real world doesn't happen a whole lot, but it is absolutely something we want to keep in mind in our designs when we're speccing out our switch hardware. Now I'm here to tell you that every one of these spanning tree versions has a lot more to cover, and we've got tons of resources available on CBT Nuggets website in order to dive deeper into each one of these. I mean, we've got whole skills on spanning tree out there. The purpose of this conversation is not to dive deep into the configuration and management of spanning tree, it's to understand how we apply this in our designs. So first of all, we need to know that 802.1d, the traditional spanning tree, was very timer based, and Cisco created per VLAN spanning tree as well as other enhancements in order to help deal with the inadequacies of traditional spanning tree. Second of all, we had rapid spanning tree come out. Rapid spanning tree gave us negotiation, for example, enabled us to converge a lot more quickly, but it didn't do anything to give us the ability to leverage some of those blocked links, in other words, multiple topologies per VLAN, and that's why Cisco still came out with rapid per VLAN spanning tree. Lastly, the industry came out with MST, and MST gives us a topology per instance, and we assign a bunch of different VLANs to each instance. But when we're deciding which of these protocols to manage, I mean, should we deploy rapid PVST, should we deploy MST, we have to consider the pros and cons to both. When it comes to MST, it's way more efficient from a usage, like an efficiency perspective, from utilization of resources. That's fantastic, but it can't be our only decision criteria. Rapid PVST is going to be a lot more comfortable from a Cisco engineer's perspective. They can do a lot more troubleshooting, effective troubleshooting on it. And so we have to take that into account when we're deciding between whether to deploy Cisco's Rapid PVST or the industry standard MST. I hope this has been informative for you. I'd like to thank you for viewing. It's time to take a look at how we implement spanning tree protocol into our network designs. In this video, we're going to explore all of the ways that we tune and tweak and configure things such as route priority level and costing of links and such. And then we're also going to take a look at some more enhancements. Yes, we just talked about all of Cisco's traditional enhancements with the old spanning tree, but Cisco still has quite a few enhancements that we want to deploy in modern spanning tree designs. Let's take a look. In most campus networks, we will have an architecture that resembles what we have here on screen, with a pair of distribution switches connecting to some number of access layer switches. In these cases, we're going to want to assign the route switch to one of the distribution switches. And keep in mind that this route is configured on a per VLAN basis if we're running per VLAN spanning tree, or a per instance basis if we're running MST. So let's say we want the switch on the right to be the route for VLAN 10. In order to make this the route, we need to set an intentional priority value to ensure that it has the lowest value, as that's how spanning tree does its elections, is by lowest value. And the recommended priority at this point would be to configure it for 4096. On Cisco switches, we have to configure priority values in multiples of 4096, which means our lowest two options are 0 and 4096 itself. In most things in networking, we don't want to take the lowest possible number, in other words, a priority of 0, and so we do one step above that, which would be 4096. Now, we also want to be very intentional about the backup route. If this switch were to go down for any reason, then we want the second distribution switch to become the route, not one of the access layer switches. As such, for VLAN 10's configuration, we'd want to configure a value of 8192 on the second distribution switch. This would be one priority value higher than 4096 because, again, we have to configure priority values in multiples of 4096. Now, keeping in mind that we have other VLANs that we need to configure this for, we would want to create a second topology. And so let's say for VLAN 20, we want to configure the switch on the left to be route. Well, in that case, we'd configure a priority value of 4096 for VLAN 20 on the left, and the switch on the right we would give 8192, again for VLAN 20 or for our second instance. As we've mentioned before, when we're load balancing our STP routes among different distribution switches, that allows us to use our bandwidth more efficiently. Because, for example, on the first access layer switch here on the left, we would block the port on the right on VLAN 20, which would allow VLAN 20 to use this path. Conversely, we're going to block the link on the left for VLAN 10, which allows VLAN 10 to take advantage of this path. If we blocked one port for all of the VLANs, then one of those links would be dead in the water. We would not use it for any of our network traffic. Now, one important note in all of this is that we need to remember that we're usually running first hop redundancy protocols at the distribution layer. And if you're working your way through the ENSLD course, then you probably know what I'm about to say, which is that we want to align the active FHRP node to the spanning tree route. So the FHRP active for VLAN 10 is going to be on the right, and the FHRP active for VLAN 20 should be on the left. This ensures that as traffic comes up, for example on VLAN 10, it's going to be able to hit the FHRP active without having to be bounced over to the second distribution switch. Next up, we need to talk about STP cost. Cost is how spanning tree figures out which is the lower bandwidth link and therefore which link should I block if I need to block one of the two. Now in most cases, we don't need to tweak spanning tree cost, but if you do find yourself in a situation where we need to block a link that spanning tree isn't blocking by default, then cost is usually how we're going to do this. And remember that lower cost is better, and so we'd actually want to raise the cost on a link that isn't getting blocked in order to block that link. Now, spanning tree has evolved over time. Originally, we had 16-bit costs, and in most cases, these are the cost values that we're accustomed to. For example, 4 is equal to a 1 gig link, and the cost of 2 would be equal to a 10 gig link. But if we do the math here, we realize, okay, well, wait a second. If I just double this and get 20 gig, that would be equal to 1. But what about a 40 gig link? And what about a 100 gig link? Well, in spanning tree world, those are all going to be equal to 1. This is why 16-bit cost values have been made obsolete, essentially, although it is still the default on Cisco switches. And so Cisco recommends that we migrate intentionally to the 32-bit cost values. When using 32-bit costs, 20,000 is the cost for a 1 gig link, for example. And so it gives us a whole lot more headroom for higher bandwidth links. Now, one note in this is that if we're going to run 32-bit costs, that cost value has to be applied to every single switch in the network. We cannot configure that in just a handful of switches. We need to make sure every switch in the environment is configured to match. Next, let's talk about STP timers. When we talk about timers, we're talking about the hello timer, the forwarding delay, the max age timer, and all of these assume a network diameter of 7. And what we mean by network diameter is the most number of hops we can take from a layer 2 perspective. So for example, in a case where we have 4 network switches daisy chained off of one another, when a packet arrives on a switch, that'd be the first switch. Then we hop over to the second switch, third switch, and fourth switch. So this network would have a diameter of 4. Now in most cases, our networks are not going to be anywhere near a diameter of 7, which means we can actually take our STP timers and tune them down. But at the same time, this is sort of a dated way of tuning our spanning tree environment because remember, we're no longer relying on timers exclusively. We are using rapid spanning tree. And so most of our situations do not rely on STP timers, and therefore, tuning the timers in an environment isn't something that we necessarily need to do. If, however, you're finding that your network has convergence issues, then this might be something to look into. Now, as mentioned in the intro, we have some enhancements we need to talk about, but these enhancements aren't like the other ones we discussed. In the last video, we talked about those fast enhancements, which improve convergence time, but these enhancements are more about spanning tree stability. We want to maintain the spanning tree framework that we've created here. In other words, we want to make sure that the root stays the root. We want to make sure that blocking ports stay in a blocking port until they really need to be pulled out of it. This is going to be broken down in a few different categories. The first category would be 2 enhancements that we call loop guard and UDLD. Loop guard and UDLD are both going to work to detect one-way communications. Think about a fiber connection. A fiber connection is actually 2 distinct strands of fiber, and if one of those gets cut off, well, that can cause a lot of problems because we're still sending traffic from one side, but the other side, even though it's trying to send traffic, is getting cut off. So maybe our BPDUs are trying to get through and they're not. And so the switch on the other end, if it's blocking that port, might say, oh, I stopped receiving BPDUs. The spanning tree environment has changed. And it hasn't. We just have one-way communications. Without loop guard or UDLD in place, a unidirectional situation like this runs the risk of taking down my network with a broadcast storm. So what's the difference between loop guard and UDLD? A loop guard is an STP enhancement. It's going to pay attention to the BPDUs and change the way that we behave on certain links. UDLD, on the other hand, has nothing to do with STP directly. Instead, it is a layer 1 communications detection mechanism. LoopGuard can detect if there's a problem with spanning tree on the other switch, whereas UDLD is only going to function if there's an actual issue with the line. As such, we usually want to deploy LoopGuard everywhere, and UDLD, even though we could deploy it everywhere, and there's no harm in doing that, the focus needs to be on deploying UDLD to fiber connections. Now, our second set of enhancements are going to be root guard and BPDU guard. These enhancements are going to protect us from a rogue switch showing up in the network and changing our STP topology. For example, what if we connect a new switch to the environment and this switch has a priority level of 0, and all of a sudden we're sending superior BPDUs up to the root? Well, if we have root guard configured on that interface, then that root switch is going to reject the BPDUs that are coming in. In a similar way, what happens if we have connections that are downstream of these access layer switches that are intended for clients, and all of a sudden a BPDU is sent onto the network? Well, that in most cases means that a client brought a switch in from their home or something like that. So now we can assume that we've got a switch hanging off of a client port, and that is not the topology that we want in this environment. And so by deploying BPDU guard to all of these interfaces, we can protect ourselves from rogue switches showing up on the network. Now when we look at these enhancements, UDLD and BPDU guard, these are going to use the concept that we call error disable. Error disable is going to effectively shut down that connection until a network admin intervenes. We can actually set timers on error disable to automatically recover. And while that can be convenient for us as network admins that the error disable state is just going to recover on its own, in some situations, especially these spanning tree ones, we don't necessarily want the error disable situation to resolve itself. We want to actually go and see what's going on and make sure that there's not an ongoing issue. Meanwhile, loop guard and root guard are going to leverage what we call the spanning tree protocol inconsistent state. It's effectively a spanning tree block state, but it is a state that will recover once the offense has been resolved. So for example, with loop guard, if the BPDU starts showing up again, well then, hey, we can pull that port out of an inconsistent state. And with root guard, once the superior BPDUs stop coming in, well at that point we can also clear the inconsistent state. Lastly, we do have one other tool at our disposal just to consider, and that would be the BPDU filter. BPDU filter is going to do exactly what it sounds like it's going to do. It's going to filter out any incoming BPDUs, which essentially disables spanning tree on an interface. We have to be very careful with this configuration because if we disable spanning tree and we form a loop through that disabled interface, well, we can count on a broadcast storm forming. There aren't a whole lot of cases for BPDU filter, but I have found situations that I've been in where we've needed to enable BPDU filter maybe on a temporary basis just to disable spanning tree, get that out of the way so we can troubleshoot another issue entirely. So as we see, there is a reason why we consider spanning tree to be a pretty complex protocol to manage, because just deploying it on its own isn't the best scenario. We want to deploy a lot of these enhancements and make sure we're configuring priority and such, and all of these things have to be taken into account. So as we review this, let's walk through kind of the major points here. First of all, we want to be intentional with configuring the spanning tree routes, so in other words, the priority, as well as the costing, by the way. And make sure to use those 32-bit costs instead of the 16-bit ones. Second of all, we want to make sure we align our spanning tree routes with our FHRP actives for the traffic forwarding scenarios that we discussed. Third, some of these enhancements, right? LoopGuard and UDLD, those are going to help us with unidirectional situations. We want to make sure that these are configured because a unidirectional communications situation that develops will take down our network if we don't have LoopGuard or UDLD in place. And lastly, RootGuard and BPDU Guard, these are there to help us protect the topology that we've established. In other words, we don't just want our network to grow organically in a way we weren't expecting. We've built this switch to be the root. Let's protect that switch as the root. Just because another switch shows up, for example, claiming to be the root, we don't want to completely reconverge our spanning tree environment just because of that. I hope this has been informative for you. I'd like to thank you for viewing. Reducing STP footprint. What do you think that means? Well, in this video, we're going to be talking about the ways that we can make our network topologies simpler, ways that we can reduce the need for spanning tree. We're going to leverage some, I call it more modern technologies, but really a lot of these technologies have been around for the last 5 or 10 years. If we take advantage of them, it's going to make our STP topology a whole lot more simple and reduce our need to rely on STP to block links. Let's take a look. This concept of reducing spanning tree footprint has been around for a long time. If we think about it, we used to have a situation where if we had 2 switches and we wanted to connect these 2 together, but hey, we want redundancy as well, so let's connect these twice. Well, a spanning tree would see that as a loop, and so we'd block one of those connections. But then someone really smart came along and said, hey, what if we bundle those connections together and do what we call an ether channel or a port channel? By bundling them together, we treat this as a single logical link, which means that, yeah, we're still sending spanning tree BPDUs back and forth, but because it's a single logical connection, there's no reason for us to block that link. And this is truly a best of both worlds scenario. We get 2 connections for redundancy, but we also get to leverage all of the bandwidth, so we get twice as much bandwidth in this ether channel. But now we have a situation where we have distribution layer switches and we have an access layer switch. Furthermore, we might have several access layer switches hanging off of this. So maybe we've got a closet with 3 access layer switches all hanging off of one another like this, and maybe we loop that bottom switch back up to the top switch. Now we have a lot of different loops in the environment, and there's no way we can use ether channels because we can't form an ether channel between 2 different switches and a 3rd switch down below. Or can we? Can we do to the rightmost diagram what we just did to the leftmost diagram? In what ways can we reduce the spanning tree footprint and possibly get rid of the loop down here below, but also the loop up here among the distribution switches and access layer? Let's start at the access layer. Let's say we have 5 different access layer switches, and we want to connect those up to the distribution layer. How would we go about doing this? And traditionally, there are 2 main ways. We could, for example, connect the topmost switch up to the distribution switches like we've done in most of our drawings to date, and then we would loop the traffic through all of these other switches down below. This is what I just drew on the previous diagram. But we do have a second option available to us, which would be to loop all the way through the distribution switches. So really now what we're doing is forming one large loop that spanning tree is going to block, probably a link somewhere in here. Maybe this link right here would get blocked in this scenario. Neither of these options are particularly ideal. If we think about the first scenario, if we lose that top switch, then hey, we've lost all of our connections to the distribution layer just by a single switch going down. However, with the large loop, this isn't ideal either because even though we can survive any one of these switches going down and still maintain connection, if we have 2 clients on these 2 switches, look at how they have to communicate with one another. They have to go all the way around the loop, all the way to the other side. This is where the idea of chassis switches and stackable switches come into play. Because if now, instead of deploying 5 switches like we just had, we deploy a single chassis switch. In addition to supervisor modules in this chassis switch, we might have 5 different line cards instead of 5 different switches. Well, even though it's 5 different line cards, this is still one logical switch, which means if I connect this upstream to the distribution switches, well, I kind of get the best of both worlds from this perspective. All of my clients downstream can communicate with one another directly without having to go upstream to the distribution switches. And furthermore, there's not much that can fail here other than potentially the supervisor going down, in which case we might want to deploy a second supervisor. But either way, we get a lot of resiliency that the first solution didn't provide. We can also accomplish this with stackable switches. By deploying 5 individual switches, but then using stackable connections and stackable technology in order to make this a single logical switch, we accomplish the same thing. Single logical switch, single logical switch. And so by uplinking to the distribution layer, again, we do have a loop among the distribution switches, but the access layer topology is greatly simplified. So our first problem is resolved. We've effectively eliminated a spanning tree loop in this topology. We no longer have to worry about the loop at the access layer. We only need to worry now about the loop between distribution and access layer. So is there anything we can do to eliminate that spanning tree loop? And indeed there is. There's a couple of options we have available to us. First of all, technically speaking, we could deploy a chassis or a switch stack at the access layer and do the same thing in the distribution layer. We could deploy a single chassis with dual supervisors for redundancy and connect these directly to each other. At this point, we can bundle these connections together. We can have as many of these connections going between distribution and access as reasonable, I suppose, and then we can bundle these together into an ether channel. And because we have one logical switch connecting to one logical switch, we don't need spanning tree at all in this environment. But the problem with this design is that most organizations are not comfortable with deploying a single distribution switch. Even if that distribution switch is a chassis switch with redundant SUPs, or it's a switch stack, either way, it's still a single logical switch, and that single logical switch could have a software failure that takes it down, for example. As such, in many network designs, we're still going to find ourselves with two separate distribution switches, even if these, again, are chassis switches or switch stacks. And these will be connected down, ideally, hopefully, to a chassis or a switch stack at the access layer. And so at first glance, there's not much we can do about this scenario to get rid of this spanning tree loop. But Cisco does give us one more amazing piece of technology that can bring us home and back to the situation here on the left. And that would be the Virtual Switching System, or VSS. What VSS accomplishes for us is it allows us to virtually stack two switches together. And specifically, we'd be talking about the distribution switches. VSS enables special management and control information to be sent between two switches such that they treat each other like they're a physical switch stack. What this effectively does is it turns these two switches into one logical switch. Again, the goal of all these scenarios is to get us to a single logical switch. And so this really is the dream, because now we have a single logical switch at the distribution layer, two physical switches for redundancy, but one logical switch. And as we've already covered, we have a single logical switch at the access layer due to chassis and stackable technology. And therefore, now these connections between the distribution and access, these can be bundled together into an ether channel. At this point, we've reduced spanning tree to the point that it's not blocking any interfaces at all. Yes, spanning tree is still running. We are still sending BPDUs between the distribution and access layer. But in the same way that if we have two physical switches with a single connection between them, yeah, we'd be running BPDUs between them, but we're not blocking either side of that link. So thanks to technologies like VSS, chassis, stackable switches, and ether channels, we can effectively reduce the spanning tree footprint to the point that there aren't a whole lot of blocked ports in our network. So when I look at this, it really boils down to two main points. First of all, at the access layer, we can greatly simplify the topology by deploying chassis and stackable switches. And second of all, to reduce the spanning tree topology even further, we can deploy VSS, Virtual Switching System, at the distribution layer. At that point, if we have a single logical switch at the distribution layer, a single logical switch at the access layer, then we can ether channel between the two. And there's no more spanning tree blocked ports in that topology. I hope this has been informative for you. I'd like to thank you for viewing. A big part of every campus deployment is going to involve power over Ethernet, delivering power to powered devices like phones and PCs and such via our Ethernet cables. In this video, we're going to discuss power over Ethernet, but we're also going to take a look at Wake on LAN, a technology that enables us to wake up PCs across the network so we can perform maintenance updates. Let's dive in. When we're talking about power over Ethernet, usually what we're talking about is taking our switch and providing power along the Ethernet line. This would be our standard unshielded twisted pair UTP type of cable. And we're going to provide DC power to some device at the end of the line. When we think about devices, we think of access points and possibly security cameras. We also think about IP phones. And there are many other types of devices that can be powered over power over Ethernet. Now, in detailing out a PoE scenario like this, we have two terms that describe the different devices involved. First of all, we have the power sourcing equipment, or the PSE. That would be the device that's providing the power, which in our example is a switch, but it could be a power injector. Second of all is the device on the other end. We call this the powered device, or PD. Now, as mentioned, we do have options when it comes to the power sourcing equipment. For example, we could use a power injector. Now, that could be a single port power injector, which is funny to say a single port because really we have two ports. What we have is we have a power injector that's plugged into the wall. This is where we get our power from. And then we've got two ports that are going to connect, one to the network and then one to the powered device. The injector is going to enable power over Ethernet on the line connecting to the powered device. And meanwhile, we allow for network connectivity between the network and the device. Now, if we have a network closet with dozens or maybe hundreds of network ports, this could get really messy if we use single port connections. As such, we can look at many different ports in a power injector, and oftentimes we're going to call this a midspan. Technically speaking, any power injector could be called a midspan, but from an industry vernacular perspective, when we talk about midspans, we're usually talking about many ports, not just the single port option that we have here on the left. Specifically, what this is going to look like is we'll have our switch. Let's say we've got a 24 port switch up here. So this is, again, our switch. And then we're going to deploy a 24-port power injector, again a midspan. But this 24-port power injector is going to look like it has 48 ports, because it's going to have 24 ports across the top and 24 ports across the bottom. What we do is we connect in all 24 of our switch ports into the top, and then the bottom is going to allow us to run all of these connections out to the powered devices. So whether it's a single port or a multi-port midspan, either way we've got options for delivering PoE out to the edge. However, one of our best options is still going to be to simply deploy a PoE switch. If we deploy PoE switches, we don't need to worry about power injectors. You say, well, why wouldn't we just do that from the beginning? Well, because what if we have traditional non-powered switches, and now we need to install IP phones or security cameras or something that we hadn't anticipated needing, and we look at our switches, and our switches either don't provide PoE or they don't provide enough PoE. Well, in those cases, we can leverage the midspan options, whether it's a single port or a multi-port. Either way, we can leverage this technology to give us the PoE budget that we require. So when speccing out switches, make sure we pay attention to the PoE budget. Just because a switch provides PoE doesn't mean it can provide full PoE on every single switch port all at once. When speccing out these switches, we need to pay special attention to the different standards that we have available to us. First of all, we have 802.3AF. This is the first standard that was called Power over Ethernet, and this provides 15.4 watts of power per port. Next up, we have 802.3AT. 802.3AT is known as PoE+, and this is able to provide up to 30 watts per port. Now at this point, the industry took a break, and Cisco got a little impatient, and so they developed something they called Universal Power over Ethernet. Universal Power over Ethernet is Cisco only, and it provides up to 60 watts per port. But the industry did eventually get around to releasing something new, and so they released 802.3BT. 802.3BT is known as PoE++, and it can support up to 90 watts of power. Now when speccing out Cisco switches, we need to be aware that Cisco kind of calls this UPoE+. Kind of an interesting one because their technology was called UPoE, but really what they're saying here is that when they have a switch that supports UPoE+, that supports not only the 90 watts of PoE++, but also the 60 watts that was Cisco specific. Cisco still uses UPoE+ to describe their switches instead of PoE++, so just be aware of that, again, when speccing out switches for our networks. Now, if we're going to look at stacking up a bunch of PoE switches or midspans in our network closets, then we need to take into account our UPS and potentially our battery backup. Technically, these are two different concepts. An uninterruptible power supply, or UPS, is mostly focused on delivering clean power to our devices. We should have UPSs regardless of whether we're running PoE in our network closets or not. But in a lot of cases, we can add battery backup to our UPSs. What that means is if we lose power to that network closet, then the battery backup kicks in, and it is able to keep all of our powered devices online, even in the event of a power outage. This is a mission-critical component of having IP phones, because back in the day, before IP phones, if the power went out, we still had the ability to make phone calls. The phone line stayed up. And if we have some kind of bad situation where disaster has struck, power is out, and we need to make phone calls for emergency services, we do not want our network phones to be down. And so now we need to have battery backup as part of our network designs in order to keep those phones online in the event of a power outage. Now next up, we need to cover a topic that is on the Cisco exam blueprint, and that is called Wake on LAN. Wake on LAN was designed to solve this problem for us where we have our users who are ready to go home for the weekend, and so they do what good users do, and they put their computers into sleep mode. And of course, over the weekend is when we want to deploy our maintenance patches, and so IT comes in for the weekend. Of course, we always have to work on the weekends, right? And so we are trying to apply our maintenance patches remotely to PCs that are in sleep mode. So the goal of Wake on LAN is to allow IT to wake up these computers in sleep mode, wake them up so that they can apply maintenance updates or whatever other reason that they want those machines to be online. The way we accomplish this is by sending a magic packet. The magic packet is not too magical. All it really involves is a broadcast packet that specifies the MAC address of the PC we're trying to wake up. But from a network engineering perspective, this is the important part. The magic packet is a broadcast packet. This means that if our server that's going to be sending the Wake on LAN magic packet is on a different network segment than the devices that we're trying to wake up, well, this is going to be problematic because the broadcast packet is going to hit the router and get cut off. If this is the scenario, then we would need to enable directed broadcast in order to support Wake on LAN. Most of the configuration for Wake on LAN will fall on the server and desktop teams, but from our perspective in the networking world, we need to be aware of how this works so when they come to us and say, hey, our Wake on LAN isn't working, then we will know to configure directed broadcast in order to get Wake on LAN up and running. So as we look at our campus designs, we need to consider PoE and Wake on LAN as part of it. Now, when it comes to PoE, we can provide that power via either a switch, a powered switch, or by using power injectors. And again, we can use a single power injector or we can use a multi-port midspan that's going to deliver power to a lot of different devices at once. Second of all, we need to know the PoE standards. We have the original PoE at 15.4 watts. Then we have PoE Plus at 30, and Cisco came out with UPoE at 60. And then we have the 802.3 BT, the newest standard that provides 90 watts of power, which Cisco does support on their platforms, but remember, they call it UPoE Plus because it's backwards compatible with their own UPoE. Third, when it comes to our network designs, we want to make sure that we're speccing out switches with the appropriate power budget. We want to make sure that the switches that we deploy can support all of the power devices that we need it to support. And we also, when it comes to our closet designs, make sure we think about UPSs and battery backup as well. Now last, when it comes to Wake on LAN, the biggest thing from a network engineer perspective is that Wake on LAN is going to require us to configure directed broadcast in order to support the process. Pretty much everything else is going to fall, again, to the server and the desktop teams. But from a network engineering perspective, if we don't do that, then the whole Wake on LAN process might not work at all. I hope this has been informative for you. I'd like to thank you for viewing. Here we are at the end of a skill, and what better way to test what we've learned than by taking a quiz. First up, out of 5 questions, what form factors support 40 gig transceivers? Now let's recall that SFP, that original SFP was 1 gig, then we had SFP Plus, which is 10 gig. Now meanwhile down here, this new SFP28, that's the same form factor as these guys up here, and it can support not only 10 gig, but also 25 gig. Next up, we have these QSFP types of optics. We have the QSFP Plus. That was the original 40 gig transceiver type, so C is a correct answer. But now we also have the QSFP28. We can support 4 different streams of up to 25 gig. That would give us 100 gig. But we can also set those streams to 10 gig each. That gives us the ability to run 40 gig on this interface type, in addition to the 100 gig, by the way. But either way, C and E are our answers. Question number 2, and feel free to pause this to read through all the answers here if needed. What factors should be considered when weighing a migration to a Layer 3 access design? Well, whether or not clients need to share a subnet, that's a pretty big deal. That is only supported in a Layer 2 access design, and so A is absolutely something we'd want to consider. Which FHRP has been deployed is not a factor in whether we're going to go with Layer 2 or Layer 3. Now C is interesting because whether ACLs have been deployed or not, it doesn't seem like it should be taken into account for a Layer 2 versus Layer 3 design. But remember, we talked about that policy sprawl, and we have policy deployed at the distribution layer. Well, if we're going to push the Layer 3 SVIs out to the edge, then that policy is going to move out to the edge as well. So where we might have had access lists on our 2 distribution switches, now we're going to have access lists on every single one of our access layer switches. And so that can get out of hand really quickly, and so that's absolutely something we'd want to consider. So A and C so far. Now D, if network loops are triangles or squares, hey, Layer 2 and Layer 3 both support that, so not a big deal. And letter E, number of access points to the network. This might have been a factor back in the day before wireless LAN controllers, because access points are Layer 2 in nature, and if we want to roam from AP to AP, then a Layer 2 access layer design would have better fit a wireless roaming scenario. However, now that we tunnel our access points back to our wireless LAN controllers, it's no longer a factor in our decisions, so E is not an option. So A and C are our answers. Next up, what factors would create a need to use MST instead of rapid PVST? All right, so let's go through each one of these. For letter A, number of VLANs in place, that actually is a factor because we recall that rapid PVST is going to make a spanning tree topology per VLAN. And if the switch can't support enough topologies for all of the VLANs, then that's a big concern. So A absolutely is a reason why we might migrate to MST, which deploys policies independent of the number of VLANs in place. Second up, the number of switches in the domain. Both MST and rapid PVST can handle all the switches we can throw at them, so B isn't a concern. Next, faster convergence is not a concern because MST uses rapid under the hood just like rapid PVST, so C, not a factor. Next, the need to support 100 gig links. This can be a factor with STP designs because if we recall that a 20 gig link is going to have a cost of 1 by default using 16-bit values, and therefore a 40 gig link and a 100 gig link, anything higher than 20 is also going to be a factor of 1. But to fix this, we move from a 16-bit cost structure to 32 bits, and we can do that with either MST or rapid PVST. So we do need to consider this as part of our STP design, but it's not going to be any different between rapid PVST and MST, so D is not an answer here, even though it is something we'd want to consider as part of our network designs. Lastly, the need to interoperate with non-Cisco switches. That should be a dead giveaway anytime we're talking about a Cisco technology like rapid PVST and an industry standard technology like MST. So A and E are our answers. Question 4. Which STP enhancements help to protect against changes in the STP topology? Up first is LoopGuard, and LoopGuard is going to be focused on detecting unidirectional links. And so, by the way, will unidirectional link detection, that's what the UD stands for. And so A and E are out. Meanwhile, BPDU filter is effectively how we disable spanning tree on an interface. That's not going to help us with this situation, so D is out. And so yes, root guard and BPDU guard, these are our answers, B and C. They help protect the topology in different ways. Root guard, for example, is going to focus on protecting us from a new root coming online, something with a superior BPDU that's advertising and saying, hey, I'm the root, not you. Yeah, we chose the root for a reason, so let's not allow a new switch to come onto the network and usurp that, take it over, if you will. And BPDU guard is going to help us at the access layer, at the edge, essentially, when somebody comes in and brings a switch from home and plugs into the network and starts generating BPDUs. We're not interested in that. So again, B and C are our answers. Root guard and BPDU guard are going to help protect against changes to the SDB topology that we have intentionally established. Last question. Which PoE power level is a Cisco proprietary technology? Well, 15.4 watts was the original PoE spec, 30 watts was PoE+, 90 watts is the new PoE++, and these three are our different standards that have been put out by the IEEE. So this just leaves the 60 watts, which is indeed Cisco's universal PoE spec. That is only going to be available on Cisco switches, and remember also that Cisco has what they call UPoE+, UPoE+ basically being PoE++, but also backwards compatible with UPoE devices. And that wraps up this quiz. If you found yourself struggling to answer any of these questions, then maybe go back and watch the video that was associated with that question in order to fill any knowledge gaps you may have had. Otherwise, congratulations on completing Design Campus Layer 2 infrastructures. I hope this has been informative for you. I'd like to thank you for viewing.